Good evening. Welcome, everybody. Thank you for joining us at the Auckland Astronomical Society, another session of Introduction to Astronomy. Tonight's talk is titled Stellar Corpses. When a star dies, the party is not over. In other words, when a star's finally done its process and it's so-called died, what's going to happen from here? Is it all over for these stars? Or are these bad boys just getting underway? It's 8 o'clock. They're just heading out the door to the big party. Let's go and find out. So the reason why I thought I'd talk about stellar corpses, you've probably all heard and read the terms white dwarfs, neutron stars, black holes. And I thought about what is needed is a discussion bringing all these terms together, but in the context of their origins, their properties, and what sort of mischief are they capable of getting into. So I'll achieve this by breaking the talk into 5 chapters. Chapter 1 will be some background information, just a bit of revision, overview of stellar evolution, how stars evolve over time, a bit about the stellar corpses themselves, and the concept of degenerative matter. Interesting topic. Chapter 2 will be on white dwarfs. Chapter 3, neutron stars. Chapter 4, stellar black holes, not to be mistaken by intermediate black holes or supermassive black holes in the center of galaxies. And in Chapter 5 will be sort of a wrap-up summary of everything and give you a little bit of homework to do. So the common theme tonight is the party is not over. So, Chapter 1, some background information. Yeah, we're going to cover these topics. Stellar evolution, where the stellar corpses come from, and the matter of degenerative matter, the stuff that stellar corpses are made of. So, bit of revision, shall we, of stellar evolution. You've seen this graph. Hopefully you've seen it many times, the Hirschsprung-Russell diagram. And you can see here on the x-axis is all the stars according to their temperatures, with the hot temperatures up here. And a sort of, what are you talking about, 30,000 degrees and about 3,000 degrees down here. And that relates, of course, to the stellar classes. And up on the y-axis, we've got luminosity, which as a factor of solar luminosity, in other words, compared with the brightness of our sun. And you'll see this nice big strip where they've got all these stars, many stars as you can, and you plot them here, their surface temperature against how bright they are. And you get this nice big strip up here. And that strip, as you'll recall, is called the main sequence. And the main sequence is where stars spend 90% of their life on that main sequence. And by definition, it is when they are burning or fusing hydrogen in their core into helium. And that state is very, very stable. Once they've finished that stage, they then move on to become red giants or red supergiants, as you see over here. And at the core of these guys, you've got helium being fused into carbon, oxygen, and in the bigger ones, heavier elements. So that's just a bit of revision of stellar evolution. Now, when nuclear fusion then in the core stops, it's about then we start talking about the end of a star's life as they enter into either a planetary nebula, which is this big thing going on over here, or a supernova explosion here. And each example of these, they leave a stellar corpse. Here, that's a nice little white dwarf in the middle of, surrounded by a planetary nebula. And you see a little neutron star in the middle of the Crab Nebula here. So the stellar corpses in the middle of these events are white dwarfs, neutron stars, and black holes, which we're going to talk of. And I want to go over shortly what type of stars give rise to these relevant collapsed remnants of stellar cores. So when the core has finished doing nuclear fusion, it collapses into a white dwarf, a neutron star, or a black hole. Let's have a look at what we call the progenitors, the term used to describe the initial star. What were the progenitors of each of these collapsed stellar cores or remnants? So start off with stellar masses. Everything is graded or compared with the sun. So a solar mass is the mass of the sun, one solar mass, and that's about 2 × 10⁻30 kilograms. So low mass stars, which are defined as stars from 0.8 up to 8 solar masses, in the later stages of life, after they've finished burning hydrogen or burning rather nuclear fusion in their cores, they start to shed off the outer layers, start to gently puff out like here until you've got here. And what it does, it exposes their collapsed, inert, inactive cores in the middle. And that little core that's been exposed is called a white dwarf. So there you go. So that's how white dwarfs come about, from these nice, gentle puffing out of the outer layers of a star up to 8 solar masses. So how about heavier stars? Well, stars that range from about 8 solar masses to about 20 solar masses, when nuclear fusion in their core stops and the core collapses in on itself, you get a rebound effect and a mighty big explosion, which I'm sure you've all heard about. It's called a supernova, and here it is here. And the exposed core at the center of one of these supernova explosions in a star from 8 to 20 solar masses is a neutron star. So that's where they come from. So how about stars greater than 20 solar masses? Yep, when their cores finish nuclear fusion, their cores collapse, you get the rebound effect and you get the supernova explosion, but the core remnant is condensed right down into a stellar black hole. So your low mass stars lead to a white dwarf, your medium stars lead to a neutron star and supernova explosion, and your really massive stars greater than 20 solar masses ends up with a supernova explosion and a black hole. So that just brings you together, so you've got those 3 stellar corpses in context of where they came from. Here it is in a nutshell. Nice little one-off diagram. I'll leave it there just for a few secs so you can look at it later on and study it. So here's your low mass stars, less than 8 solar masses, red giant phase, nuclear fusion stops, the outer layers just start to gently puff out. That whole process takes about 10,000 years or so. It's not a sudden big explosion. It's a gentle process. And there's your nice exposed, inert core of a collapsed core called a white dwarf. Here's your higher mass stars, become red supergiants after the main sequence. They go boof into a supernova explosion, which we went over to last month, and you're welcome just go on the site there and have another look over that talk. 8 to 20 solar masses ends in a neutron star, that's the core exposed, and very high mass stars end up as a black hole at the center. So yeah, here's a concept, what I want to talk about, degenerative matter. The reason it's important, essentially, it's the stuff that stellar corpses are made of. So stars, as I've alluded to before, they are propped up because they've got a huge lot of mass and gravity is trying to condense them down, but they are supported from collapse by nuclear fusion in their core that's driving energy out. And that's called a state of hydrostatic equilibrium. And that's how stars spend most of their life. So when fusion in their core stops, the core collapses. And the question is, what does it look like? The bottom line is they're made of degenerative matter, these condensed, collapsed cores. So let's go and have a closer look and see what degenerative matter is all about. So there you can see the importance of it. So this is what normal matter, that when we went to high school, we all learned about normal, ordinary matter. And we saw little sort of atomic nuclei full of protons and neutrons, a nice tight little ball there with these electron orbits all around them. And whatever the matter was, they were, let's say it was a solid, they're all nicely lined up in a lattice and so on. So there's 2 important concepts as I start to talk about degenerative matter. First of all, when that star core collapses, matter gets compressed, really, really compressed, whereby its normal structure and order is totally disturbed. Nothing like you'd see here on Earth. The second important concept I want to introduce right now is called the Pauli exclusion principle. That is whereby no 2 fermions are just subatomic quantum particles, of which include electrons and neutrons are both fermions, examples of those. So no 2 electrons and neutrons, can simultaneously occupy the same quantum state. In other words, the same area, the same energy levels, and so on. Two electrons can't overlap into one another. Two neutrons can't overlap into one another. They can't occupy the same state at the same time. So they've got to keep away from one another. That's called the Pauli exclusion principle. That's an important concept to get right now. So when one of these low mass stars, up to 8 solar masses, when its core starts collapsing and compressing, what happens is you start getting what we call electron degeneracy. We're about to get compressed more and more and more. Instead of all these electrons all here zipping around with plenty of space, and all the atomic nuclei separated and so on, these whole sort of normal atoms like this, you start getting it really, really compressed, where essentially you get a lattice of just nuclei, protons and neutrons, all nicely bound up together. You just get, they're all squashed together. And instead of the electrons being in their nice orbits, they essentially just are running amok, running all over the place at random. Why are they doing that? Because the area is so compact and they are obeying Pauli exclusion principle. That's what they're doing. They are not allowed to be overlapping into one another. So you've got your nuclei all together and just these electrons darting round and round and round. And that pressure of the electrons dancing and running amok all over the place, dipping and bopping and diving and ducking, that creates a resistance which then props up that core, that collapsed core of a low mass star up to 8 solar masses. And that's what a white dwarf is made of. It's essentially electron degeneracy, a state where everything's been compacted so much, where electrons are running crazy, and that's sufficient pressure, resistance of those electrons to hold it up. That is what's going on inside a white dwarf. So how about if you've got a star greater than 8 solar masses, in particular between 8 and 20? You've got a bigger star, a bigger core. So you've got more compression going on. That compression overpowers that resistance from electron degeneracy. And what happens then is the electrons get rammed inside the protons to create neutrons. So instead of a nice sort of normal structure we're used to here on Earth with your nice atomic nuclei and your atoms and your atomic orbits here off your electrons, you're moving into this case where the atomic nuclei are all squashed up together, electrons ducking and diving in between. So the electrons now get shoved into the protons and you just get a thick lattice or a dense compressed state of just straight free neutrons. And those neutrons also have to abide by the Pauli exclusion principle, which says in quantum physics, no 2 electrons can occupy the same quantum state. So this time it's the neutrons ducking and diving, dipping and bopping, avoiding one another, and that creates a resistive force that stops that core from collapsing any further. And that essentially is what neutron stars are made up of, neutron degenerative matter. So that gives you a little bit of background, this revision of stellar evolution, the 3 main stellar corpses, where they fit in, where they came from, and the concept of degenerative matter. Everything gets compressed and squashed in that Pauli exclusion principle. Let's move on. White dwarfs. Let's have a look at these guys. So I'll split this up into the origin, just to recapping the proposed structure, where they sit on the Hertzsprung-Russell diagram. What's our closest white dwarf? Let's have a look. And here's the interesting bit. When you start getting white dwarfs in close binary systems, that's when the party really kicks in. And we have novae and supernovae type 1a. And if you saw last month's talk, you'll remember all those. We'll revise those. And of course, white dwarfs are involved with mergers, with interesting things going on. So white dwarfs, as we talked, are essentially the core remnants of a low sort of to medium mass red giant that's started off in life as between 0.8 and 8 solar masses. It's got a core, nuclear fusion stops, can't hold itself up, so the core contracts. And instead of being normal matter, it goes down to the state of electron degeneracy. And in that mass of that star, electron degeneracy is sufficient to prop up and hold that core and keep it stable. And you've got yourself, ladies and gentlemen, a white dwarf. So what happens then, as we've talked about, the surrounding layers of these stars just gently puff outwards to expose that core of electron degeneracy, aka your white dwarf. And that takes a few thousand years for all that to happen and that white dwarf to be exposed there. So you've seen these pictures. I love these pictures. Aren't they gorgeous? When you see all these nice pictures in here, often people say, oh, is that a supernova? No, that's a planetary nebula. And it's a sort of low to medium mass star. It's outer layers. This is what's happening here. Here's your white dwarf. The white dwarfs are really, really hot. And essentially they're compact. It's carbon and oxygen is what's going on in here. That's in a state of electron degeneracy. They're really, really hot. So you're talking 30,000 odd degrees. So they emit a lot of ultraviolet light, and that ultraviolet light then ionizes, in other words, kicks an electron off the atoms that are sitting out here, and all this is all the outer shells of that star over about 10,000 years or so. It's all gently puffed out and shed. The hot core illuminates it and ionizing it, and you get that lovely picture. And there you have your white dwarf in the middle and your planetary nebula. So now when you see those sort of pictures, you know exactly what's going on. You can say, aha, that is the white dwarf, that little central bit there, and it's in a state of electron degeneracy. I know all about that now, and I know why we've got this lovely, lovely picture going on here. So that's just proposed what they look like. The carbon and oxygen core is probably in a crystallized state, and most of it in the middle, due to those compression. Size, how big is a white dwarf star? They're actually not big. They're only about the size of the Earth, to give you an idea. The mass range is quite wide. They range from about 0.17 solar masses up to about 0.33. Most of them fit in there. In fact, the lion's share of them are actually in a smaller range from 0.5 to 0.7 solar masses, with a large peak, if you can imagine it, by far the largest number of them, 0.6 solar masses. And interesting enough, counterintuitive, the higher the mass of a white dwarf, you get more compression, so it actually gets smaller. So if you see a white dwarf significantly smaller than the Earth, you know that's got a higher mass than if you see one that's, say, slightly higher than you'd imagine the Earth to be. So just a bit of counterintuitive, but when you stop and think, well, it's all about compression going on to create this degenerative electron degeneracy matter, it all makes sense. So where's it going to sit, white dwarfs? Here we go. They sit down here. They're really, really hot, as we've talked about. They get their surface temperatures up to 30,000 degrees. That's why they illuminate all the nice material around them to create those beautiful, lovely pictures. And they're relatively dim. Why are they dim? Because they're small. They're only the size of the Earth. So they're hot and they're dim. And that's where they sit on the Hertzsprung-Russell diagram. What's our nearest white dwarf? Well, Sirius. Here's Sirius, you know, Canis Major, that's in the summer sky. That's the sort of the dog beside Orion, the hunter. And the brightest star in the sky there is Sirius. Sirius is actually a binary star system. It's two stars. You've got your big main star here and your small star here, Sirius B. That is a white dwarf, and you can see it here. It's about 8.6 light years away from us. A light year being the distance that light travels in a year, which is about 10 million kilometers. So that's relatively close in the big picture. That's our closest white dwarf. Okay, so what happens with white dwarfs if they start getting into a close binary system? And you recall last month we talked about how our sun just quietly travels solo on its own around the galaxy. You get a lot of stars are binary stars where they're going around one another, a central point of gravity as they rotate. And then a close binary is you get two stars really close to one another as they go, really tightly gravitationally bound. And the thing is, white dwarfs in a close binary can do one of two things, if you recall from last month. They can go nova or supernova. Let's talk briefly about nova, just recapping. There's a nova here. Nova means new star, and you can see here a new star's appeared. That's called a nova, and that's because a white dwarf is in a really tight, close binary with another star. You'll recall we talked about how you get a red giant sitting next to this white dwarf. You get a spillover of the outer layers if it's close enough, forms a hot accretion disk around the white dwarf, just like that. What happens then as the accretion disk material gets hotter and hotter, and the inner contents start falling onto the surface of that white dwarf. And what happens then is, remember that white dwarf, the surface is hot and it's small and compact. So you're getting the hydrogen that's flowing more and more is stacking up onto the surface of that rotating white dwarf. And as it does so, it gets compacted tighter and tighter and tighter. The temperature goes up, up, up and up. And suddenly you reach a crucial temperature whereby that thin hydrogen atmosphere covering or smothering the surface of that white dwarf gets hot enough, bang, it starts fusing hydrogen into helium. And the whole outer atmosphere of that white dwarf just goes poof and lights up. And that is called a nova. A sudden release of energy. And here it is. Here's a nice little picture here. There's some Hubble telescope pictures. It's just been ignited. The white dwarf here has just been ignited. And here's this layer coming off here, being expelled into space. So what happens here, it is only that outer layer or hydrogen atmosphere, if you will, of the white dwarf that explodes and goes boof. So the white dwarf survives, and with time, the process repeats itself. That same red dwarf donates more outer layers of mainly hydrogen into an accretion disk, falls onto the white dwarf, heats up, critical temperature, goes boof. And that's called a nova. Now, as mentioned, white dwarfs in a close binary system can also go supernova. And here's a supernova explosion here next to its host galaxy. And you can see these babies are so bright, they outshine their host galaxy. So let's have a closer look. So we're just going to back up a little bit to explain about what's going to happen. The crystallized white dwarf core, they always have a maximum of 1.4 solar masses. And you saw how that one of those previous slides, they ranged from sort of about 0.17 right up to about 1.3 or so. They don't quite get up to 1.4 solar masses because a white dwarf, as it approaches 1.4 solar mass, becomes unstable. Remember all those electrons ducking and dipping and diving and dipping and bopping and so on around the lattice, in that state of electron degeneracy? As the pressure goes up, because more mass, it gets more and more condensed, those electrons have to start approaching the speed of light to avoid one another. The whole thing becomes unstable and the whole star catastrophically destroys itself in one mighty explosion. And here it is here. You got your red dwarf feeding material to form an accretion disk. Slowly the white dwarf gets more and more massive. It hits 1.4 solar masses. And the whole lot just explodes. One big, massive explosion. It's called a Type 1a supernova. And if that's new to you, just have a look through last month's video and explains all further about these as it compares them with other supernova. So the key points here is it's a one-off explosion. The white dwarf just gets demolished, does not survive. Because they all occur at roughly about 1.4 solar masses, the same physics, the same quantities are going on, so it's a nice consistent luminosity. Furthermore, these are the brightest of all the supernovas, so they're really, really bright. So astronomers use them to serve as standard candles at long distances, cosmological distances from galaxies far away. And the theory is, if you know how bright something is, when you see a 1A supernova go off, you know how bright it actually is, you measure how bright you see it from Earth, and it's pretty easy then you can calculate the distance to these faraway galaxies. Here's a nice little, what they call a light curve. This is where you plot time against the brightness of a supernova. You can see it getting brighter and brighter and brighter here early on. Those 1A supernova get to about 10 billion solar lumini. In other words, they're 10 billion times brighter than our sun. And you can see it dipping away here. So they are the brightest of all the supernova, those 1A, and that's why and it's just brilliant how you know exactly the physics of what's going on, because they're all from the same conditions. So you know how bright they are. Okay, now white dwarfs also can merge with other stars, can merge together, and typically they'll often go on to form a neutron star, or they can, if they reach the critical mass, if they happen to reach 1.4 solar masses, they can go into a type A1A supernova as well. The merging of two white dwarfs recently has been linked with, you've probably heard of this phenomenon, which they're still trying to work out, where you get these fast radio bursts, little bursts of radio waves. And one of the leading contenders is that it could be the merging of two white dwarfs. So they're actively involved in merging as well, which can create supernovae or to form a neutron star. So as you can see here, they're far from complacent, dead corpses. We also corpse, dead body, lifeless. Oh no. No, far from the truth, the stars. Yeah, now, last year there's a paper came out where these guys had discovered a most odd, peculiar looking star. When they analysed it further, they pretty much concluded most likely what had happened is two white dwarfs had merged, the material had mixed together, combined mass, and the right conditions were there. Nuclear fusion, reignited. You had a new, albeit oddball star that had formed from fusion of two white dwarfs. How's that? Something new and interesting. So let's get just summary of white dwarfs. So their progenitors, in other words, what did they originally come from? Low to medium mass stars, 0.8 to 8 solar masses. And of course, that means our sun is well and truly in there. This is what's going to happen to us one day. You get these planetary nebulas, the outer layers puff out, and they expose that central white dwarf, which is the collapsed core, and that core is in a state of electron degeneracy. White dwarfs, when you get them in a close binary system, they accrete material, typically off a red dwarf, and it can be repeated explosions of the surface of the white dwarf, or novae, or one big catastrophic 1A type supernova. And they can do mergers to form neutron stars, go supernova, or a new star. So they're quite active little fellows. So let's move on to neutron stars. That's the second of our stellar corpses. So we'll briefly talk about where they came from, the proposed structures of what they think most likely is going on the inside. We'll talk about how they rotate really, really rapidly, and their rate of spin can change. It can go up, it can go down, all sorts of things. We'll talk about magnetars and starquakes. We'll talk about how, because they rotate with strong magnetic fields, they can be radio pulses. We'll talk about when neutron stars are in close binaries, they can appear as X-ray pulses. And we'll talk about mergers and kilinovae. So let's get moving along. So this is just that revision again. So here was your white dwarf coming from your low to medium mass stars. Here's your higher mass stars, 8 to 20 solar masses, red supergiant, boof, supernova explosion, and the central collapsed core of these guys here is a neutron star. So how big do these guys get? About 1.4 to 3 solar masses. Because remember, a white dwarf, a core of a white dwarf with electron degeneracy cannot get up above 1.4 solar masses. It becomes unstable. So these guys are 1.4 to 3 solar masses, and they're stable in that state. So as we talked about, they're the core remnants of these high mass red supergiants after they've exploded, gone supernova, because nuclear fusion has ceased in the core. And this is an X-ray image of the Crab Nebula, which is in the Taurus constellation in the summertime. You can see it, and you can see the the neutron star sitting right there, emitting X-rays. This is a fantastic image. This is all in X-ray wavelengths. I put 1054 here. In 1054, I think it was the Chinese who noted, oh, there's a big new bright star in the sky. And later years, modern astronomers realized that must have been a supernova those guys were looking at. And when they looked at that exact same spot that was described, this is what they found, the Crab Nebula. So it's a supernova remnant, and right there in the middle is your neutron star. So let's go and talk more about these babies. So as we've talked, you get compression. Anything greater than a 1.4 solar mass, it compresses down. The electron degeneracy is not enough to hold it, so it compresses down tighter and tighter. And the electrons, instead of dipping and diving and so on between these sort of nuclei, instead the electrons get shoved, get rammed right into protons, and which creates a neutral neutron, and this is what your neutron star looks like in here. It's a state of neutron degeneracy. And this soup of free neutrons are zooming around, and as we've talked about, they also are obeying the Pauli exclusion principle. They've got to keep away from one another. So that resistance props it up and keeps it supported. So a little bit about, so how big are neutron stars and so on? I've mentioned the masses rather, about 1.4 to 3 solar masses. How about their size? Instead of being the size of the Earth, which is a white dwarf, these guys are the size of about an average city. In other words, 20 kilometres across, radius of 10 kilometres, diameter of about 20 kilometres. And suddenly you've got up to 3 solar masses. In other words, 3 suns jammed into a space the size of a city, an average city. That's pretty dense, that's pretty compact. They're so dense and so compact that 1 teaspoon of a neutron star on Earth would weigh about 1 billion tons. The gravity, because they're so dense and such high masses, but also the surface of them is so close to the center, the gravity is immense on their surface gravity. And here's another little interesting bit, food for thought. If you had an object, you placed it, hypothetically, 1 meter above the surface of a neutron star and dropped it, when it hit the ground 1 meter later, it would be traveling at 1,400 kilometers per hour. That's the acceleration. But what would happen, because you're dealing with such huge surface gravity and such intense gravitational forces here, because you've got something so dense and so close to its center, it's not very big, the tidal forces involved would just rip you apart. It's a process called spaghettification, which we'll talk about shortly with black holes. So it would just get ripped apart. But interesting enough, those fragments, shall we say, would be hitting the surface at 1,400 kilometers per hour. Amazing. So these really are fascinating. They're the most densest, second only to black dwarfs, black holes, which we can't really identify directly and so on. In terms of stellar objects, these are the most dense, compact objects known. So what's going on inside? And I put proposed complex in a structure because it all comes about from modelling. They sort of base it around where we know the general idea of what conditions must be going on. They match it up with their observations, form hypotheses, and continually matching off theory against observations. And from there, they develop these models. And it is quite complex. On the internet, you'll see all sorts of interesting little sort of cut-through diagrams like this. There's 2 key points that I want you to remember. And of course, you can freeze this, watch this later on if you want to have a closer look and have a good scrutiny of it. But just for now, for this sort of time while we're talking now, there's 2 key things I want to impart. One is it's got a thin, solid outer crust. Yeah, and that's solid. That is relevant. You'll see why in a minute. So that's solid, this thin outer solid crust. And that is composed of free charged particles, in particular electrons and protons. And importantly, they can be extracted off the surface later on. That's important. The second key point amongst all of this is their interiors it's a superfluid, in other words, really, really loose, no resistance, no viscosity. It's a superfluid soup of electrically neutral, and that's relevant, neutrons that are created as this. Remember to also these neutron stars, actually, as you're about to find out, these neutron stars I'm about to show you, they're rotating, they're spinning really, really rapidly. And you've got this friction-free sort of whirling soup of electrically neutral neutrons, and they create a lot of like whirlpools within them as the whole neutron star whips around. The other thing about the interior is you've got these superconductive areas of protons, which are positively charged, and they, because they've got electrical charges, they are able to drive and anchor down really strong magnetic field lines coming out of these neutron stars. So we're going to talk about all this shortly, but I just wanted to show you it's quite complex what they think's going on in here, but there's just 2 things to remember. A thin, solid crust of electrons and protons that can be removed under the right conditions, and an interior that's very liquid. And it's swirling around at high velocity, and it can do all sorts of interesting, strange things. And it's got the ability to anchor down strong magnetic fields, really anchor them down into the neutron star. So let's move on from here. So neutron stars, two key factors, which I've already mentioned one of them, they rotate really, really rapidly. They can quite happily rotate more than 1,000 times a second, what's called millisecond neutron stars. You imagine that, second, goes around 1,000 times, quite happily. They've also got very powerful magnetic fields, up to 1 billion times more powerful than our sun. How did this come about? And that's why I've put at the top here. Neutron stars, as you recall from that stellar evolution, they come from these big, really large these red supergiants. And to give you an idea how large these red supergiants are, you put an average one of these into the middle of our solar system, its outer sort of surface, if you will, can go out to Jupiter, the orbits of Jupiter, Saturn, Uranus, and so on. Some of those really, really large ones can be the size of our solar system. That's how large these are. These red giants, before they go supernova, of course, they're spinning around. They got magnetic fields. Most stars do. All stars rotate. And there's a concept called conservation of angular momentum. And that refers to, a lot of you have probably heard this already and seen this nice picture, that angular momentum is the rate at which something is spinning multiplied by the factor of how wide or how large something is, how its radius, if you will. And a classic example of this, you get your ice skater here. She's holding her arms out, spinning it sort of, so fast. She brings her arms in to reduce her width, so to speak, and she starts spinning faster and faster and faster. So that is called conservation of angular momentum. So going back to the slide, it follows that if you've got one of these huge big red giants that you can see here, here's the sun up to a giant star, and you bring that down to here, and these supergiants, they're huge. So you've got one of these massive red supergiants spinning around yay fast. You suddenly shrink this thing down from the size of our solar system to the size of a city on Earth. You imagine how much faster this thing is spinning, faster and faster and faster. So that is the key why these neutron stars are spinning so fast. And that's a really key property to neutron stars. The other thing is these big red supergiants, they have magnetic fields. And also, as they start to shrink down and start to reduce in size, down to the size of a city, the magnetic fields get more intense and more powerful. So it is because of this one thing that they started off so big, they've been shrunk and compressed so small, they rotate so rapidly, and they have really powerful magnetic fields, up to 1 billion times the magnetic fields you see on the sun. So those are two really key points. Let's move on. So that's a nice little image here. So these stars, I want to introduce the story now, is they're spinning really rapidly, but the spin doesn't last forever. Like us, they all start to lose a bit of energy and they slow down. They dissipate their energy in neutron stars when they're young, spinning really fast, and then they get slower and slower and slower over millions of years. You're talking here. Over millions of years, they start getting slow. And that's called spin down. Now, they can also get a spin up. I think I mentioned earlier at the introduction. They can speed up. And this happens if you get a close binary system, such as this red dwarf here, and it's next door, and it's feeding material onto an accretion disk, which you saw the similar thing happen with white dwarfs. But as that material builds up an accretion disk, and it feeds on to the pulsar, or the neutron star in the middle. I've jumped the gun a little bit by using the word pulsar here, but it jumps onto these neutron stars. And as the neutron star accumulates more and more mass, it starts speeding up quicker and quicker and quicker and quicker. And you end up with these, and I'll come to the word pulsars in a minute, but you come to these millisecond neutron stars that are spinning, thousands of times per second. So that's how you can get a spin up. So spin down occurs naturally with time. A spin up is when you're in a closed binary system and mass gets fed on to the neutron star. Now, there's another little interesting concept of glitches, and that refers to, they see neutron stars that seem to get a sharp jolt, where they can suddenly increase in spin, and at times, just as quick as they get a sudden spin up, they get a quick spin down and brought back. And the model's suggesting what's causing that, and here's some of the relevance if we talk about what's going on inside, is you get these whirlpools of this superfluid neutral neutrons that are moving so readily, and they move from the inner crust. You might get a whirlpool or elongated whirlpool of neutrons from the outer crust, leans on and attaches itself to the inner crust. Remember, amongst all this, these guys are spinning really, really quickly. And when it attaches, it gives the neutron star a good jolt forward and quickly increases its rotational rate. And that's called a glitch. And some of these glitches to spin up are followed quickly by another glitch to slow them down. The general thought is probably a second elongated whirlpool of the superfluid, super neutral neutrons, just lagging a little bit, takes its time, but that also attaches to the crust and jerks it back to slow down. And I was thinking about this, and a good friend of mine, Jay, from the Hibiscus Coast Astronomical Society, she said to me a really good analogy that she ways to think about what's going on of these elongated whirlpools of neutrons is an analogy on Earth as a twister or a tornado. They're elongated whirlpools going round and round. They've almost got the properties like of gas and liquid. You know, you've got vapor, you've got water in there going round and round, a nice mobile mixture. They move very quickly with little resistance. You see them darting across as these guys are chasing these twisters. And they're quite happily, they can briefly attach themselves. They'll attach themselves to a camper van or a house and pick it up and plonk it down somewhere else. So I thought that's, if you're trying to, image in mind what's going on inside here, think of them as twisters. These twisters have got properties, they're neutral, they're mobile, they can quickly attach to things, and they attach to the crust and they can speed up or quickly jolt the speed down. And they're called glitches. We've spoken about neutron stars having very strong magnetic fields, once again, because they've concentrated down. So the magnetic field of that original progenitor star is more intense, more concentrated. Some neutron stars have really, really strong magnetic fields, up over 1,000 times more than your average neutron star. And these guys are called magnetars. I've actually put here too is to explain how they get so strong magnetic fields. We talked about the conservation of angular momentum with reducing size. Well, magnetic flux of a star is related to its inverse square of its surface area. So as the surface area gets shrunk down from a big red giant, the size of our solar system, down to something the size of a city on Earth, you can imagine that's a huge reduction in surface area of that star. And you square that and inverse it, and you can see why suddenly these magnetic fields become so intense and so powerful. And that's one of the reasons why you can get these magnetars. And the word magnetar, when you see it now, you go, okay, I know what that is. It's a neutron star, but really, really particular, intense, strong magnetic fields around it, up to 1,000 times a normal neutron star, which in itself has a pretty powerful magnetic field. Now, the reason I introduced magnetars is because these magnetars themselves are strong magnetic fields, and you've got these neutron stars spinning over to 1,000 times and so on. And remember, I mentioned this crust here was solid, this outer crust of electron and protons, it's solid. And you've got something that's spinning so quickly, intense magnetic fields and so on. You've got things like spin down processes going on, spin up processes going down. Stresses develop in that thin crust on the neutron star and suddenly release themselves, which then in turn, as you get that deformity of the crust, a little fracture occurring in the crust, if you will, like an earthquake, a little fracture develops and you get a disruption of those intense magnetic fields. And when that happens, you can get sudden bursts of intense energies. And that's where you get gamma ray bursts. And you recall that gamma rays are the most intense form of light, electromagnetic radiation. And they call them gamma ray bursts, where you get a sudden burst of intense gamma rays coming from a region in the sky. And they're split into long duration and short duration. The short duration ones are quick bursts, less than 2 seconds duration. And they can either repeat or not repeat. And the repeating ones are thought to be from magnetars that are spinning rapidly. That thin crust develops a bit of stress fracture, if you will, get some distortion and disturbance of the magnetic fields, a sudden release of high energy. So that is the theory behind what's causing these short duration gamma ray bursts. And it's, of course, a consequence of the high magnetic fields, of the high rotation rates, and their thin, solid crusts. So we've talked all about the rotation rate, magnetic fields, and the consequences. How about radio pulses? So I'm introducing this term pulses now, and hopefully you've heard of the term pulsars. Well, it's all about neutron stars have been observed in some circumstances with pulses of radio waves being transmitted towards Earth, just coming in pulses, pulses, pulses. So what's all that about? They're called radio pulses, or sometimes just shortened to pulsars. So here's why. Let's just go through this step by step. Neutron stars, as we mentioned, rotate extremely rapidly. Round and round they go. They have powerful, intense magnetic field lines. And here's the bit. Remember I said those inner fluid layers, there's protons in there which are positively charged, are wonderful at creating and anchoring down in the solid crust magnetic field lines. So magnetic field lines form because you've got rotating charged particles, and they can quite happily create these really intense magnetic field lines and anchor them down to that solid crust. And remember, the crust, I said, also consisted of free electrons and protons that can be extracted. So you're getting the whole picture here going on. So these powerful, well-anchored, rotating, rapidly rotating magnetic field lines then create electric currents. And these electric currents can quite happily pick up electrons and protons from the crust of the neutron star and accelerate them to what we call relativistic velocities. In other words, close to the speed of light. And what do magnetic fields do? They direct everything back to their poles, their magnetic poles. So you get these magnetic fields and these rapidly rotating neutron stars. They pick up the electrons and protons, accelerate them to use velocities, all funnel or direct them to these magnetic poles where they are all ejected out from the poles. And they form what we call bipolar jets. In other words, here's the two poles, and you've got jets coming from out of each pole of charged particles. And that gives rise to what we call synchrotron radiation, commonly in radio waves from the magnetic poles. Now, I'm not going to leave you there. I'm going to jump ahead as a little side note, because you may be thinking, what is synchrotron radiation? So synchrotron radiation refers to the fact that you've got magnetic field lines like yay, and you've got charged particles like electron protons. When charged particles are moving through a magnetic field, they experience a force. That force encourages them to spiral round and round and round and round the magnetic field lines. And when you get charged particles accelerating, i.e. changing direction constantly, they emit light, electromagnetic radiation. It's actually right across, that electromagnetic radiation usually can be right across the whole spectrum, right through visible, ultraviolet, X-rays and so on. But by and large, predominantly, it's in the radio wave wavelengths, typically. So that's what synchrotron radiation is. So you've got these bipolar jets, you've got these charged particles that have been picked up off the surface, are getting spun out huge velocities close to the speed of light, spiraling in intense magnetic fields. They are emitting mainly radio waves as they do. And if you happen to get a star whereby the magnetic pole is not aligned and identical to the rotational axis of the star which is whipping around, you end up getting these beams of synchrotron radiation sweep across the sky like that. And if that, much like a lighthouse, if we happen to be in that line at which the radio waves are sweeping around, we see pulses. And it's like a lighthouse. I think I've got that on the next slide. Yeah. If the beam sweeps across our view, we see a lighthouse. And the same here. It's like a lighthouse. The light was shining through here. It's shining through. You see it here. It swings around like that. And back again, you see it again. And that's just the same beam of light going round and round. But from your perspective, all you see is little flashes off the light, analogous to a lighthouse beacon. And they're called radio pulses because we just from Earth are seeing pulses of radio waves. And that's what's going on in these radio pulses. Now, interesting enough, these radio pulses, of course, I've described here, you can see you don't need a binary star, another star. That just happens on its own with a young neutron star, nice strong magnetic field, rotating quick enough. And if the beam is now visual, our field of view, we see that. But you can also get X-ray pulses. And that is when you get a neutron star in a close binary system. And what is happening here is you get this material from your red giant. It's attracted to the neutron star, starts forming this accretion disk here, and it's really attracted. So remember that the gravitational field in these things is very, very intense in these neutron stars. So you get this hot matter going spinning faster and faster and faster in this accretion disk. Then the inner material, as it starts to fall onto the surface of this rapidly rotating neutron star, remember, they have really intense magnetic fields. So the magnetic field picks up on these charged particles coming off the accretion disk and doesn't let them just fall at random onto the neutron star. It captures them. Here it is starting to fall on here, magnetic field line. The intense magnetic field line captures these charged particles from the inner part of the accretion disk and drops them right on the surface, splat. And when you get this hot material, just splat. And remember I told you about a neutron star? If you just drop something from a meter, it hits the surface, what, at 1,400 kilometers per hour? So this material is hitting at huge velocities, and that bang impact is powerful enough where it creates X-rays emitted. But where is that sort of dumping, if you will, of this accretion material? It's all getting on the magnetic poles because the magnetic field lines is dumping this material right on the magnetic poles here. Another example of it here. So you're getting these X-ray being emitted just from the magnetic poles, and it's coming from the accretion disk. It's getting directed by the magnetic fields and dumping right on those magnetic poles. So you're getting X-rays visualized at these magnetic poles as the neutron stars spin round and round. And once again, if we happen to be in the right alignment where we see these hot spots radiating in X-rays, we from Earth see these pulses of X-rays coming from neutron stars. So just something different. They can present as pulsars, either radio, if they're solo, or in a close binary, they can make us see X-ray pulses. Now, neutron stars can quite happily merge. We talked about that last month. Get these two neutron stars, they have to be in a close binary together. They start merging, they lose energy, and they can't start moving closer and closer, and they merge. And last month, we talked about kilonovae. The word novae meaning new bright star in the sky, kilo meaning 1,000, because they're about 1,000 times brighter than your average nova. And you recall we talked about this environment, this explosive environment of these two neutrons merging and going boof. And this is where a lot of your heavy elements are created, what they call nucleosynthesis. And here's the periodic table that we looked at last month. Here's merging neutron stars. So this refers, these colors here coded, refers to the origin of all these elements. So you'll see here the bright orange, all these elements here are made through the process of nucleosynthesis. We're going to talk about that next month, how it actually happens. But you just need to know that when neutron stars merge together, create a nice big explosion called a kilonova, and that's where important, your gold and your silver and so on, that's where these elements are formed in these processes. So just to recap, neutron stars, they're from high mass stars, 8 to 20 solar masses rather, where you get the supernova explosion and that central core that's in a state of neutron degeneracy. They're compact, small, the size of a city. They rotate up to 1,000 times per second, very intense magnetic fields. You get magnetars. They're the most extreme magnetic neutron stars. You can get these little star quakes, little fractures in the thin, rigid crust, which creates these repeated bursts of gamma rays. Where you get singular neutron stars, they can present themselves as radio pulses, or in a binary system, they can present themselves as X-ray pulses. And there's your kilonova with the nuclear synthesis, this making of important heavy elements. So you can see there, neutron stars are pretty busy people. Just because they've died and they're now called stellar corpses, they're far from lifeless. Let's move on to stellar black holes. We'll talk here. We're going to talk about we'll just recap what were their progenitor stars, the original star they came from, how they warp space-time. We'll talk a little about some of the components, in particular the event horizon. We'll talk about the peculiar things when you approach the event horizon. Everyone likes talking about that. What happens to stellar black holes when they're in binary systems, and then a bit of fun with the emerging. So you've seen this. Do not apologize. I show this simple diagram many times per set of slides. It's so good. So here's your new star that's formed, high mass stars, goes to a red supergiant, the core collapses, fusion stops, core collapses in itself. You get a massive rebound explosion called a supernova. And the high mass stars, greater than 20 solar masses, their core collapses down to form a dark black hole. Now, mine is covered up here, and I think you'll see here is the mass of these black holes is greater than 3 solar masses. That's the core of the black hole. I don't know if it's visible here. Part of my screen is covered up by a small little window. But the bottom line is, remember these white dwarfs are up to 1.4 solar masses. The neutron stars were 1.4 to 3 solar masses. This is referring not to the progenitor star, but to the collapsed core. Your black holes have a mass of greater than 3 solar masses. So we've talked about that. So you get this gravitational compression of the core. And the mass of these circumstances is so great where it's gone into a stage of electron degeneracy, but it's kept going. The force is still great. So it starts then pushing electrons into protons to create neutrons, or a state of neutron degeneracy, with the resistance created from the neutrons zipping around trying to avoid one another, and consistent with the Pauli exclusion principle. But the mass is sufficient where it doesn't even care about that. It just keeps going and squashes that sort of lattice of free neutrons, even just squashes that into oblivion, called a singularity or a black hole. More detail of what's going on there, it's not really fully understood. A lot of the laws of physics and so on starts to break down when you get to those points, but we all understand the general concept that it's just broken, it's being crushed to something infinitely small. And you may remember from Einstein's general theory of relativity that masses bend and warp the fabric of space-time, and that's the basis behind your gravitational waves and so on. And black holes, the idea behind them is they squash and distort that space-time so much, whereby the gravitational forces right inside is so great that nothing, not even light, can get enough energy to accelerate out of that gravitational well. Another simpler way of looking at it is talking about the escape velocity. And escape velocity is a function of how dense and compact something is at its surface. And of course, the more dense and compact and higher mass it is, the escape velocity gets higher and higher, and it gets harder and harder to get off the surface of that body. The escape velocity of a black hole just happens to be greater than the speed of light. So not even light can escape them, hence the name black holes. So that's a little introduction there to them. So the event horizon, there's the singularity right in the middle of the black hole. They don't understand it too much more than that. The laws of physics break down. But you've got this event horizon. And the event horizon is the boundary of this region where light cannot escape. And it varies from black hole to black hole. It's also known as a Schwarzschild radius of the event horizon. The size of the event horizon increases with the mass of the black hole. So the bigger the mass of that black hole, say a 4 solar mass black hole is going to have a larger Schwarzschild radius, hence larger event horizon than, say, one of a 3 solar mass black hole. Yes, strange things start happening at the event horizon. So just recap here. Here's your event horizon. It's the region which light cannot escape, because anything inside this event horizon, light gets pulled in, it can't get out. Light outside the event horizon, light can quite happily escape. And at the event horizon, light is either neither falling in or it's not falling out. Light is stationary. It gets suspended there. And it's because of this principle, really neat things, strange things start to happen. And everyone loves these questions. They say, what if say an astronaut hopped out of a spaceship, or in a spacesuit, whatever, in a spaceship, started heading out towards a black hole, heading towards the event horizon, and you were sitting back watching, and what would you see? It's because of this distortion of the fabric of space and time getting pulled and stretched apart that time starts to slow down, what they call time dilatation. That's involved with Einstein's theory of relativity and special relativity and so on. Read up about that. But in short, to an observer, and you're watching an astronaut heading towards that, as he gets closer and closer to that event horizon of that black hole, he's going to start getting redder and redder, colder and colder. Everything starts slowing down for him. He'll start getting dimmer and dimmer, and he'll start moving slower and slower and slower. So redder, colder, dimmer, moving slower and slower, and until he just gently fades, and he'll just sit, and it's sort of almost completely out of sight, sitting on that. He'll just hover there as his clock, according to your perception of him, will just come to a halt. And you'll see a very vague, dim, cold, red astronaut hovering, just sitting there as his clock stops. How about for the poor astronaut? Of course, his clock is going to run as normal. So he's just going to, as far as he's concerned, he's just heading towards that black hole. But it won't take long before he goes through that process of spaghettification. And that's the concept of tidal forces. Because you're dealing with such intense, strong gravitational forces, the gravity pulling at his feet are going to be a zillion times more powerful than the gravity, say, pulling at the other end, at his head. And for that reason, it just gets stretched out and just ripped apart by the tidal forces. And the process is called spaghettification. So he wouldn't know too much more about it. 1 minute, he's quite happily heading towards that black hole. Next minute, he's just shredded to nothing. He won't be coming back to tell you about it. Okay, so that's what happened with the event horizons. Everyone loves to talk about that little topic. So what happens when you get a close binary system with a stellar black hole? You start getting what they call X-ray bursts. So here's our red dwarf again. Our red giant again, pardon me, our big red giant sitting here. You've got this stellar black hole here. The huge gravitational forces attracting all this outer layers, which is predominantly hydrogen from this red giant, forms this hot accretion disk. But the disk starts getting closer and closer to that event horizon, and here the whole velocity of this accretion disk is going faster and faster. The particles are getting more and more compressed. They're colliding more and more to extremes. You start getting temperatures at the inner part of this accretion disk of millions of degrees. What happens when you get particles at those temperatures? They start emitting energy in bursts of X-ray radiations. And indeed, that was the first real evidence in the 1970s through X-ray observation, just through X-ray bursts. They could see them in the sky. In fact, my article on this month's journal thing about the history of X-ray astronomy talk a little bit about that. I think it's probably more about it next month. But anyway, we talk about how these early days they saw these little bursts of X-rays in the sky. And they soon worked out over time what these were. These were stellar black holes in a binary system with something like a red giant or a red supergiant, accretion disk forming around it, hot, compressed inner gases going up to 1 million degrees, spitting out bursts of X-rays. And of course, black hole merging. You've all heard with gravitational waves was all the big news about 5 years ago. And how black holes and neutron stars, for that matter, they sort of could quite happily, close binary systems, they start getting closer and closer together to merge. And in the process, they dissipate energy, and that energy is ripples in the fabric of space-time, which we pick up as gravitational waves. So even if they're not doing anything else like emitting X-rays, you get two black holes together in a close binary system, and they start having fun playing with the fabric of space-time. So black holes, their progenitor, or the stars of which they came from, are the really high mass stars greater than 20 solar masses. The core collapses, get a rebound effect, get a big boof, supernova explosion, and that collapsed inert core is known as a black hole, where it's just because of the sheer size of it, the sheer gravitational forces, it's compressed itself past electron degeneracy, past neutron degeneracy, into a point of singularity. There is the event horizon, which the size of it correlates with the mass of the black hole, from which nothing escapes. You get strange observations because of the distortion, the fabric of space-time. And then when you get a black hole in a binary system, you can start getting X-ray bursts. And of course, you also can get mergers of the two black holes. You can quite happily get mergers, and those create those infamous gravitational waves, which we all love reading about these days. So, summary and homework. Oh my God, how many times have you seen this tonight? But you see here, here's the progenitor star, less than 8 solar masses, ends up at this lovely, beautiful planetary nebula, white dwarf, high mass stars, red supergiant, goes supernova, and it leaves behind a neutron star. If the original progenitor was between 8 and 20 solar masses, you're looking at a neutron star up to about 3 solar masses, that's the core, and the stars that are originally greater than 20 solar masses end up as the collapsed core ends up as a stellar black hole, which is greater than 3 solar masses. That's a lot to take in. That's cool. It's going to pause that for a little while so you can go back over it and play it and take all that on board. But that diagram says it all. It's bringing everything together. So white dwarfs, key messages here, they are in a state of electron degeneracy. So the electrons zipping around after the compression, trying to avoid knocking into one another and occupying the same space. That gives that resistance, that gives it support. Neutron stars, things have progressed a little bit greater than that. The electrons are shoved into protons to create neutrons. The neutrons are trying to avoid one another, and that creates that state of neutron degeneration or resistance to prop it up. Stellar black holes, of course, straight to a point of singularity. And as you can see here, yep, just because they're called stellar corpses, they're not lifeless. The party is not over. As you can see here, the white dwarfs can go on to form nova explosion. These really super bright 1A supernova, they can go through mergers and create new stars and explosions. These neutron star stellar corpses, so-called lifeless bodies, no, they're not. They can create radio pulses. If they're on their own, they can team up with a close binary and form X-ray pulses. They can combine and merge 2 neutron stars to create all the important heavy elements in the universe. And of course, black holes can give rise to these strange event horizons, X-ray binaries, these bursts of X-rays merging to form gravitational waves. So by no means the party is not over. It's when these stars, so-called, end their lives, as we often use the term when they go boof into an explosion or a supernova explosion or a planetary nebula. These stellar corpses is the wrong word because corpse implies a lifeless body, doesn't it? Now, these guys are just coming alive. The party is just getting underway. Now, when you do get home, you're probably already home, of course, but you know what I mean. If you want to read a little bit further around this, read up more about white dwarfs and what sort of state they're in, the different white dwarfs and planetary nebula. Why? Because that's the fate of our sun. Our sun is 1 solar mass. Remember, 0.8 to 8 solar masses ends up as a collapsed white dwarf core in that beautiful, picturesque planetary nebula, as you see here. So that's something, if you've got to think, well, this is vaguely interesting, this sort of stuff, that's a good thing to look at. So thank you for watching, and I hope you've seen tonight that when a star dies, the party is far from being over. The party is just getting underway. So at this stage, Steve, just any questions out there at all?
Yep, we've got a few questions. I'm actually going to start with a question from me, and since I'm on the microphone, I figure I can ask a question. Sure. Are there any circumstances where a white dwarf could accrete mass, and instead of going into a Type 1a supernova, it could go into neutron degeneracy and turn into a neutron star?
Yeah, look, I'm unsure if there's anything like that written in the literature and stuff, but you think to yourself, that's a good question. My understanding, once it's that core of oxygen and carbon, that particular lattice, soon as you get more than 1.4 solar masses, now the whole thing just becomes unstable and rips itself apart, as opposed to going on, which is a very, that whole core collapse, we're talking less than 1 second. It's just an instantaneous thing when the neutron star is forming. But when you've got a lattice of electron degeneracy and you keep adding mass onto it, as soon as it reaches that 1.4, the whole lot just becomes unstable and blows itself apart. I think because you've got no other mass to contain it and allow it to keep compressing down.
Okay, cool. Thanks for that. Question from John Drummond over in Gisborne there. He says, does the magnetar need to have a fracture in the crust aimed at Earth to be detected as a gamma ray burst? If it repeats with a 2-second period, does this mean the blast rotates across the Earth like a scanner?
Yeah, so I don't quite get that. So could you just read that question again, slide? Just trying to take it all in.
Does the magnetar need to have a fracture in the crust aimed at Earth to be detected as a GRB? So we'll start with that one.
Yeah, because we've got to see the GRB, the short duration GRB. There could be GRBs going off in all directions, and we don't necessarily see them. If they're not orientated, it could be going the other way. So, yes, having said that, it's less than 2 seconds, and these babies are rotating pretty quickly. But yeah, the gamma ray burst has got to be orientated towards us for us to see it, which implies the fracture in the crust has got to be, such that the gamma ray burst is heading our way. So there's gamma ray bursts, I'm sure, heading all over in all directions, and it comes down to a thing like the pulsar. We only see it as a pulsar if we happen to be in the correct line of sight.
Cool. And he says, if it repeats with a 2-second period, does it mean the blast is rotating like a scanner? I assume he means that the star is rotating at that period.
Yeah, good question. Because normally they just classified, gamma ray bursts are classified into long duration, short duration, and usually it's just a quick burst. And I wonder if he's implying that if you get a star that's rotating, say, 1,000 times per second, could that be the same gamma ray burst that's still sub 2 seconds? But it's usually a steady sort of burst. That's a hard question to answer, actually.
That's cool. Another question from Jonathan Park. He says, are all pulsars neutron stars, and are all neutron stars pulsars?
Yeah, good question, Jonathan. All pulsars are neutron stars, absolutely. That radio waves, those bipolar jets. All neutron stars aren't pulsars, however, because to be a pulsar, a neutron star, first of all, it's got to have a bit of youth behind it in the first, say, million years or so. It's got to be rapidly spinning rapidly fast enough to pull all those electrons and protons, charged particles, off its crust. And it's also got to be young enough to have an intense magnetic field. As neutron stars slow down, they start getting to a point where they haven't got quite the spin rate to become a pulsar, and the magnetic fields lose their intensity as well. And you're talking sort of something like 1 billion years or so, that sort of ballpark. So it's got to be young enough where it's rotating rapidly enough, the magnetic field is still intense enough, and its axis of its axis at which those bipolar radio jets are going out must be such that that beam of radio synchrotron radiation is coming in front of our field of view, where we get that pulse every few seconds or milliseconds. So it's got to meet those two criteria for becoming a pulsar. Now, you might have a neutron star that someone in another part of the galaxy says, oh, there's a pulsar. we're looking at that same neutron star and we don't see a pulsar because its axis is orientated differently. So it's got to be, the neutron star's got to be young enough to be rotating fast enough, strong enough magnetic fields, and the beam's got to be orientated such that we see it as a pulsar. It's a good question.
Thanks for that one, Chris. Another one from Max Mayer, who says, how can you see a neutron star if it does not emit light? And if you cannot see it, how can you infer its internal structures?
Yep, good question. X-ray and radio. You don't see them exactly in optical wavelengths very well. You do see them. You saw that picture of the Crab Nebula. That was an X-ray. So neutron stars emit X-rays quite happily. They actually have, like, sort of looking for a better word, stellar winds. They do actually give out a little bit of wind as well. That wind will emit X-rays and tends to also ram into the supernova remnants, lighting it up, creating X-rays. You're starting to see those jets of synchrotron radiation, which I also implied can get in X-rays. Right, you can get X-ray, optical, ultraviolet radio waves, and so on, and you get those accretion disks as well, which quite happily light up in X-ray wavelengths. When you're looking at those, you see there's a close binary companion going around one another. You can deduct from the motions, you can deduct the masses of each of those two companions, and you start seeing an accretion disk emitting X-rays. You know there's only one thing it can be, a neutron star. So you're quite right. You don't see the neutron star directly in optical wavelengths, but you can see it directly in X-ray wavelengths, and you can see it indirectly in almost, radio waves right through to X-rays. And just to recap, you could see in that Chandra telescope X-ray image of the Crab Nebula, you could very directly see that neutron star. So, yeah, good question. You can't see it in optical wavelengths, but you can in X-ray wavelengths.
Thanks for that. And the final question, again from JD. He says, great talk. Can you explain about Hawking radiation escaping from the region of a black hole, please?
Yeah, okay. I actually did have a slide on that when I took it out. So Hawking radiation is referring to an activity or something you can observe with black holes, and that is right at the event horizon. There's a concept in quantum physics whereby particles and antiparticles can suddenly appear into existence, and within a certain time frame they can quickly annihilate one another and disappear again if within a certain time. So instantly particles and antiparticles forming and annihilating again. If you get, say, some particles forming through this quantum effect, you get particle and antiparticle. If you suddenly get instantly as it forms, but it happens to be right on the event horizon, you can get the antiparticle shoots into the event horizon, and before the two have got time to quickly annihilate one another, one shoots into the event horizon and one gets back out the other way. So, in other words, if you look at an event horizon, you can see this quantum effect of, and I don't know how that's exactly, but I believe that they actually have got proof of it. Hawking first hypothesized it many years ago and said, look, if there's some sort of quantum effects going on here of particle generation, then it makes sense. If they're right on the event horizon, before they've got time to annihilate, they go their separate ways and one appears to come out of the black hole. And indeed, I believe there is observational for evidence that Hawking radiation, which there is, does indeed occur. So from our perspective, it looks like there's radiation, there's particles, radiation coming out of the black hole, but that's what's going on.
Thank you very much, Chris. That's the end of the questions for tonight. Thanks for a super interesting and informative presentation once again.
Thank you very much, and have fun, everyone out there, and be aware of those star corpses. Thank you.